In this lesson, we'll discuss what happens when a block of ice is placed into a bath of water. This is a phase change problem, specifically heat of fusion. The question reads, an insulated container holds 3 kilograms of water at 25 degrees Celsius. 1 kilogram of ice at 0 degrees Celsius is added to the mixture. In the first part, what is the final temperature and composition of the mixture? In other words, they're asking how much of that ice will remain, if any, after they've been placed together. So the very first thing that I want to do is refer back to a formula that we used in our previous video, and it is called the heat capacity formula shown on your screen right here. The heat capacity formula is written as Q, which represents the amount of energy, heat energy, and that can either be in calories or joules, and that's equal to the mass times the specific heat capacity, this factor. That's the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. And over here is the difference in temperature. Now with that, I can calculate the amount of heat the water, which is at 25 degrees Celsius, will be releasing to the ice, which is at 0 degrees. Let me show you how to do that. We have Q is equal to the mass of the water being 3.0 kilograms, multiply to its specific heat capacity. And in this problem, unlike in the previous, I'll be using the version of the specific heat capacity that has joules per kilograms times Kelvin, as opposed to when it was in calories per grams times degrees Celsius. They are the same thing. You can convert one form to the other. But I want my answer to be in joules as opposed to calories. So using that version, I have 4,200, and that's rounded. If you want a more specific value, it would be 4,184. Joules per kilogram times Kelvin. Notice how the units for a kilogram cancel out, and that's what we're looking to happen. And now we multiply this by the difference in temperature. So the water is 25 degrees and the ice is 0 degrees. The final temperature being 0 minus our initial 25. Remember that the change in temperature is equal to the temperature final minus temperature initial. So subtracting these, I get negative 25 degrees Celsius. And keep in mind that the units here are in Kelvin. So if I were to convert 0 to Kelvin and 25 degrees to Kelvin, I would still end up with a difference of negative 25. So rather than writing down negative 25 degrees Celsius, I'll just write down Kelvin. Negative 25 Kelvin. That cancels out with that. And multiplying this out, we end up with a negative value, and I'll show you. Now that negative value is expected. It's negative 315,000 joules. This is expected because a negative Q value, as indicated over here, suggests that the object released thermal energy to its surroundings. So with that being said, we can now use this energy value to find out how much ice it can melt. What I'll do is create a second equation where I have Q is equal to the mass of ice that will take in this much energy, times the heat of fusion for ice. The heat of fusion for ice is different than the specific heat capacity. It's usually much larger than the specific heat capacity. This is the amount of energy needed to convert the solid phase into liquid phase. And most textbooks will report that that value is roughly 3.3 times 10 to the power of 5 joules per kilogram. I'll take this value right here and place it into this Q value, and I'll get rid of that negative because whenever your Q value is positive, it means that the object is gaining thermal energy. So we will take away that negative, and it's not important for this calculation. I'll write down 315,000 joules is equal to M, that's an unknown, times 3.3 times 10 to the power of 5 joules per kilogram. We have to solve for M, and that can be done by dividing both sides by this factor. So let me go ahead and show you what that is. So we'll divide this by 3.3 times 10 to the power of 5. And we get a mass of 0.95 kilograms. So 0.95 kilograms of ice will absorb 315,000 joules of energy. That means there will be some ice left over. There will be 0.05 kilograms of ice left over after this 1 kilogram block of ice is thrown into this water. Because there's ice left over, that means the water doesn't have enough thermal energy left to convert the rest of the ice. Therefore, there will be no further heat transfer because both the water and the ice are at the same temperature. The final mass of the water will be 3.95 kilograms from its original of 3 kilograms and only 0.5 kilograms of ice. In question B, if the amount of ice is reduced to 0.50 kilograms, what is the final temperature of the composition? If it's reduced to 0.50 kilograms, then all of that will be melted. In fact, in part A, we learned that 315,000 joules is enough to melt 0.95 kilograms, and this is well below that mark. All the leftover energy will end up in the water, so this time we should expect the final temperature to be between 0 and 25 degrees. So what we can do to answer this question of finding the final temperature, what I can do is rewrite this equation where I have Q is equal to the same two factors that we started with. And this gets multiplied to, this time we know that the water will not reach a final temperature of 0 degrees. So I'll write down T for the T final minus the initial of 25 degrees Celsius. Now you're probably wondering, this is in Kelvin and that's in degrees Celsius. Because we're dealing with differences here, it really doesn't matter. So I'm going to go ahead and change this to degrees Celsius. It's the same thing in this particular case. Now because the water is releasing its energy, make sure that the Q value is negative. That will ensure that this T value is less than 25. All of this energy will go into two things. It will go into melting the ice completely, and it will go into raising the temperature of the water. Therefore, I will take this expression and make it equal to those two other factors that I was explaining. Let me show you what I mean. So I'll rewrite this down here. Notice that I made it negative. That will go into melting the ice. And to melt the ice, we use the expression mass times the heat of fusion. So the mass of the ice is 0.50 kilograms times the heat of fusion. And just to be clear, this will give us the amount of energy needed to melt the ice, plus an expression to represent the energy needed to raise the temperature of water that is at 0 degrees Celsius. The mass we'll use is 0.5 kilograms, and the formula we'll be using is the heat capacity formula. Multiplied to the specific heat capacity of water being 4,200 joules per kilogram times degrees Celsius. And we don't know the final temperature. We know it's going to be between 0 and 25 minus the initial of 0. If we solve for T, we will find out exactly what question B is asking us for, the final temperature. And this is very similar to the problem that I did in the previous video, which is now linked on your screen. So rather than wasting your time, and it's really not that hard, you multiply these out, 0.5 times 4,200. You multiply these out, which gives you a constant value. Multiply these, expand, and solve for T, which should give you a value that is around 10 degrees Celsius. If you're having trouble solving for T, leave a comment below and I'll gladly show you a breakdown of how to solve the rest of this equation for T. And there you have it. Now you know how to solve phase change problems, specifically those dealing with heat of fusion.